All right, a little quick one here. This is just if you're struggling with some of the homework questions, I just wanted to hop on and do a little bit of examples here. So I'm not actually going to run the exact questions in the homework, but we'll do something similar. So this is just Google Colab on this side and the homework questions on this side. So we're going to start with question 2 and just try to work our way through some of these. All right, so I'm just going to load the most of our Python modules here and mount to Google Drive. So set this all up, and then we're going to be connected. So once we get connected, we're going to run, we're going to load our data set. So I've specified the file path, and then I'm just going to sample from the data set. But when you run this for yourself, you will not run this part. So you can get rid of that if you like. All right, so we'll just run this, and then it'll just print out the columns for the data set. If we wanted to see the data itself, we just do data.head, and it puts 3 extra columns over here. These are just blank. So the main data we're looking at are world return and Italy return. Okay, so question 2a is about which is the sample model. So we have one thing as the outcome variable. We have our intercept, and then we have the coefficient on the predictor variable, and then the error term. So you'll just pick which one of these is the sample model. But for the coding portion, what we're looking for is the standard error. So we're looking to calculate the standard error of the world return coefficient. So this is, on our beta 1, we want the standard error. And then we also want the confidence interval for the intercept. So these are 2 different coefficients and the variability in them. And then we're looking to figure out which one is which. Okay, so the way we find this is we run the model. So what we're doing, we want to run a regression using Italy returns as the outcome variable. So this is going to be our y variable. So we put this as Italy return as the y variable. So this is our syntax for taking the column for Italy return from the data set. And then for our predictor variable, we have world returns. So we have data and world returns. And we want an intercept, so we're going to add a constant. Okay, and you could show this if you like, but we're just going to take these x's and y's and put them into our model and fit it. And then we'll just print this out. Okay, so this is not the answer. You would get different numbers. But you'll remember so we're looking for the confidence, the standard error of the world return coefficient. So to find that, we just go down to world return. This is the coefficient, and then we could find the standard error. So this is sort of the S in our hypothesis testing. But here we're just looking at the variability in the coefficient itself, and not the population estimate like we did with hypothesis testing. Okay, so nice. So that's the first part. And then the second part is to find the 95% confidence interval for the intercept. So for the intercept, we have our constant term. We have the coefficient, so it's hitting the the y-axis at negative value. But then Python actually just spits out for us exactly the confidence interval we're looking for. So the 95% confidence interval is this thing. All right, so we have our 95% confidence interval and the standard error for the world return. So then we can answer this question. So the third part of this question too is to use the fitted model predict Italy's return for this given world return. So we're going to, we're looking at essentially like a line, and then we're going to plug into that line some x variable. And the x is world return at this negative 0.1. So then we're calculating both the point estimate and the 95% prediction interval. All right, so a little bit of code here. And Gemini actually can do a lot of this for you, so rely on that heavily. But we've gone through and fit the model here. So what we want to do is just get the prediction, and that's what we're calling with this this function. So what it takes in is two values. One is going to be the value of the constant term. So we're saying with a 1 here, we're saying that we do want to include a beta 0. So this is our beta 0. And then we also want to put in the world return prediction. So we're looking for, what's the x variable? And that's this thing. So when you put this into your homework, you'll add a negative. But I'm just going to run this as a positive. So it'll give us a different prediction value. And then we have it predict the mean. So this is our mean prediction is the predicted mean. So this is just some code for that. And then for the second part, we're asking for the both the point estimate and the 95 prediction interval. So we're plugging in the x, it tells us exactly what the prediction is, but then because it's a model, there's some variability, which is coming from just the variability in the regression model. Okay, so then to get that, we can put in a confidence interval of 95. I'm just going to put in a confidence interval of 99. Okay, and then we'll just spit these out, and it gives us these things. So this is the predicted value. So we've built this model, and now we can make a prediction using that model. And then we can talk about the range, the confidence interval around that model. Okay, nice. So question 3, so we have this data. We're wondering about this linear regression between inflation and growth rates. So the first part is to write out the estimated linear relationship using these things. So you'll just take the constant term and the growth term, and like we've done, you just plug those into the relationship using beta 0 and beta 1. And then for B, we're going to use the model to calculate the expected inflation for a country with a 5% money supply growth. So what I've done here is, I'm not going to actually run this, otherwise it would print out the answer to the homework. So what you'll do is, so we have a growth rate, which is our 5%. And then what we want to do is just write down the equation. And so what running this would do is print out for us the predicted y variable, which in this case is inflation. So we plug in the growth that we're looking for, and that will spit out for us the y variable, which is inflation. Nice. Okay. And then this last part is a simplistic monetarist. That's a typo. Monetary theory claims that beta 1 is equal to 1, and the relationship follows this relationship here. So it's a linear relationship, and our beta 1 is 1. So we're asked to test this regression result. Okay, so the way we do this is, just like we test any hypothesis. So what I'm going to do is actually test a different hypothesis, and then we'll run these things. So we have the standard error that's given to us from for the beta 1. We're going to, what we're fundamentally trying to do is test whether beta 1 is equal to 1. Or as I'm going to do it, whether beta 1 is equal to 2. And just like we do with hypothesis testing, what we're trying to do here is test whether this beta 1 is very close to our null hypothesis. And we have the measure of variability in our beta 1 given to us by the standard error. So we have this variability around our beta 1. We know what the estimate of beta 1 is, and we just want to test how far away is our null hypothesis. So maybe what I'll do is I'll write the null hypothesis, and we'll call this 2. And so what we're doing here is just constructing a z-score, just like we've always done. So this is the difference between the estimate, our beta 1, maybe we call this beta 1 hat, and our null hypothesis. We also have our standard error. So just like we do, we will run this thing, calculate the z-score. All right, so when we actually run this z-score, so I'm going to put in a null of just slightly different than 1. We have a z-score that's equal to 4. So remember the interpretation here. A z-score of exactly 4 would tell us that we are 4 standard deviations away from each other. So beta 1 hat is 4 standard deviations away from the null hypothesis. So that's what this is telling us, and we know that the null hypothesis is, below the beta hat. So, if we were drawing this distribution, we would be the beta hat would be above the z-score. Sorry, the beta hat would be above the null hypothesis. Okay, so the question is, how likely is it that we are making a mistake by saying that these things are different? Another way of thinking about this is that what's the probability of the z-score being what it is? So 4.6. So what's the probability that that the null hypothesis is in the tail of the distribution around the beta 1 hat? Which is essentially, how likely are we to be more than 4.6 standard deviations away? And we know this is going to be very unlikely because 4 standard deviations away is much further away than our 3 standard deviations, which would give us a 99% levels of confidence. So we should expect something very small. So what I'm going to do is we're going to look at the area. So this is a positive value. So we can look at the area in the tail on the negative side by doing this thing, and then we'll just multiply that by 2. So we're getting both tails. So when we run this, we get an incredibly small number. So this is 3.7, but this is in scientific notation. So this is we're going to move the decimal place 6 times. So this is just an incredibly small number. The number you get in the homework is not this small. So just be careful with that. Okay, but this is a very small number, so we can confidently reject that these are the same. All right, so question 4. So we have a real estate agent talking about housing prices. We want a 99% confidence interval for the slope coefficient. So the slope coefficient is this thing. So it's telling us, and this is sort of a weird result here, but it's telling us that the number of houses is negatively related to the price of the home. So as you add more houses, as you add more rooms, the price of the house goes down. So it's sort of a weird result. But, the world isn't always exactly as we think it is. Okay, so the first thing to do is to calculate the 99.7% confidence interval for the slope coefficient. So what we're going to do is use 3 standard deviations. And again, like we're being, a little imprecise about the number of standard deviations and the level of confidence, but this keeps our life simple using the empirical rule. Okay, so we have our beta 1, we have our standard error, and just like we always do, we're going to construct a confidence interval around the beta 1. So the standard error, we multiply that by 3 and subtract that from beta 1, and then we do the same thing but add it to beta 1. And this gives us some confidence interval. All right, so then for a house with 5 rooms, we're going to calculate the probability that it sells for more than 270. And so what we want to do first is we want to calculate the prediction. So we have, we say, our x variable is 5 rooms. So like we did before, we're going to make a prediction given some particular x value. We also have the standard error. So like we've done before, we're going to be able to construct a z-score. We have the variability, which is coming from the variability around the model. And then we have our prediction. So this is all very nice. And what we're asked is for this thing. We want what's the probability that y hat is greater than this thing, than this 270,000. Okay, so we take our y hat, which we've predicted here. So this is just running some math to get a number. And let's actually print this first. So let's print out y hat, and that gives us this thing. So this is our predicted value for a house with 5 rooms. And so that's nice. Let's hide that though. So let's get the z-score, and then let's also print the z-score. So to get the z-score right, we take the y hat, and then we subtract off the null hypothesis, which is the thing we're trying to test. And then we also have the standard error of the model, which is given to us right here. Okay, so then we'll just run this, we'll print the z-score, and then we'll check the number. Okay, so we have negative 1. So we're saying the prediction and the null hypothesis are 1 standard deviation away from each other. So we should already be thinking that this is going to be it's going to be difficult for us to reject the null in those sort of terms. But we could also just check the probability that the house will sell for less than this. So this is just the error, the area in the tail below. And so we could run this if we'd like, but I will let you do this on your own. All right, I'll see you in the next one.